So my name is Doug Hanks. I work here at Juniper. I work in the campus and data center business unit. So we make the hardware, the software, and the solutions for the entire company for our data center products. So now I want to talk to you guys a little bit about the QFX5100, which enables us to build out these large-scale infrastructures for multi-stage cluster networks. So it's always good to pare it down to the actual products, because that's what you get your hands on anyway. So we got 3 models. These are shipping as of today. The first one is the 24Q. It's just your basic 32 by 40 gig 1U switch. So these are all Trident 2 based switches. This one in particular, I believe, is the BCM, I want to say 56860 chipset, as well as the rest of them. The next one is the 48S. So it's your typical 48 by 10 and 6 by 40 going up. And the last one is actually a trick, because this next one is exactly the same as the first one, just in a different form factor. And you may ask, how's that possible? So if you have 32 by 40, what you can do is you can take 24 of those 40 gig ports and use breakout cables, and you get 96 ports. And then you're left with 8 by 40 gig going up. So it's the exact same thing as the third option. So we just go ahead and break it out for you in a 96 by 10 and an 8 by 40 instead of using breakout cables. So if you really want that type of form factor or real estate, you can have that. So traditionally this will be a spine switch, a leaf switch with the 48S, and again another leaf on the 96S. So the key thing about this box is that once you invest in it, you've got a lot of different options. So we've got 6 primary technology choices. So up top are the Juniper architecture. So these are our proprietary turnkey fabrics. So we can do a virtual chassis fabric we talked a bit about in the multi-stage session. We have a QFabric node. So if you have QFabric, you can use these new switches into that architecture as well as the basic virtual chassis. Now we have the open architectures as well down at the bottom. So it can obviously operate as a standalone switch, L2, L3, whole 9 yards, or we can do MC lag. So if you got some third-party switches going southbound, we can use MC lag and LACP to bring those into the loop via L2. And the last one is the CLOS architecture, which we talked about a little bit before. So 6 overall options. So we talked a little bit about virtual chassis fabric. I want to do a double click in terms of what that actually is to give you guys some additional detail. So what is it? So we start back off with the 4 spines and 16 leaves. So you do the math, it's 20 nodes. So this is the ceiling of virtual chassis fabric today. And I believe in August of this year, we're going to raise that ceiling again, and we'll go to 32 nodes. So we'll keep on raising that ceiling as we test and qualify this going forward. And we'll kind of do an incremental approach to make sure it's solid. Now what we'll do is that we'll use our existing virtual chassis technology to encapsulate this topology right here. And the difference is that virtual chassis kind of stops at 10 nodes on the access layer, and the virtual chassis fabric includes the spine and the leaves. And again, we go through those 20 nodes, so hence we call it the virtual chassis fabric. And this is a full ECMP topology for L2, for L3, for multicast. It's a single point of management, and it's pretty cool. The thing here is that we can actually do ISSU on this entire topology, because we virtualize the control plane of the switch. I like to joke around and say it's actually not even a switch, it's more of a server, like Greg was saying, because we really bumped up the specs in terms of the power in there. So we have SSD hard drives, Sandy Bridge cores, whole 9 yards, DDR3 memory. So it's really more of a server that happens to be a switch.
So real quick, because we've talked about virtual chassis,
yep,
the fabric side of this will not extend down to the current edge switches like the 4200s and stuff, correct? This is purely a data center play with the QFX type stuff that you're telling us about.
Yeah.
All right.
So Actually, you can include some other models into the same fabric, and those two would be the older QFX5100 and the 3600. And if you wanted to add native 1 gig to this as well, you can add the new EX4300 into the virtual chassis fabric. So there's some more options for you.
Okay.
So you're not just limited to these new 5100s.
Okay.
So if you take a look, the reason that this is plug and play, you simply just kind of throw these switches together, you plug them up, power them on, and it'll automatically detect, who's my neighbor, what model is he, how many ports, how many links are going between each nodes, and you can get some very interesting cabling happening. So for example, over here with L1, this is a simple leaf, and it's going up to these 2 spines. I happen to do this on purpose, so I got 2 links going from the leaf going to the spines. You normally wouldn't do that, but if you did, we've got a concept called automatic trunks. So it'll automatically detect these trunks no matter where it's at in the fabric, and so we'll automatically aggregate these links. So that's going to be on a per hop basis. So your next door neighbor will actually aggregate those 2 links, and then we've got a concept of a remote destination aggregate as well. So in this example here, L1, if it wanted to go to L4, we would create a virtual remote destination trunk going between these 2 PFE chipsets. So we've got the local ones here in the teal color, T1, T2, T3, and then these red lines going from L1 to L4. That would be our remote trunk as well. We'll do that for every single node in the fabric. So no matter where you're at, you're going to have these automatic trunks in the background between any point in the network. So this is how we get full ECMP going across this thing. And we actually, to the previous comment, we use IS to do this, to find the topology, neighbor discovery, and we add some custom TLVs to accomplish this.
Okay, so let me go back to my earlier point. You're doing custom SPB. This is exactly what was broken down for us yesterday. You're just doing custom SPB across this in order to accomplish this.
Yeah.
Because you're saying you're using IS, which is what SPB is, and then you add some secret sauce to it. So
yeah.
Congratulations, you've made my argument for me that SPB is valid.
At a very small scale.
Yeah, that's offline, but yeah, you're doing SPB.
But that's
Okay.
that's the same underlying stuff that we've been doing in virtual chassis since the 4200 came out in 2008. We've just changed it now, so instead of using the backplane cables, we're using 40 gig cables. We're adding the additional. So yes, we're doing SPB, but we have been doing that protocol since 2008.
It's a good point. It's a really good point. Yeah.
So with this diagram here, we have the 3.
Hipster virtual chassis fabric, right?
So we have the 3 trunks coming out of L4. One of them goes to S1, 2 of them goes to S2. If there was a second trunk going to S1, would those also have be grouped northbound?
So if there's a second trunk going from L1 to S1, you said?
No, S1 to L4.
Oh, S1 to L4.
Yep.
Yeah, so there would be no automatic trunks here because it's just a single link going down to this guy. But if there was 2 links here, would make a T4 right here, for example. But in that case, it's just 1 link. Yeah.
So but when you're doing your ECMP, are you taking into account, in your example, you have 2 trunks that appear to be over 2 different bandwidth paths. So is there some intelligence there to say, if I'm going from L1 to L4, I should probably only send half as much up through S1 as I do through S2?
Yeah. So we have full visibility of what bandwidth exists between point A to point B and all the intermediate hops. So we can basically do one lookup on the ingress, and basically for every flow or every packet, we can say this should be your final destination with these particular intermediate hops in between, and we'll base that off the amount of bandwidth. So we can do unequal cost load balancing if we needed to.
Which is where I was going. So,
Right.
So you are, because the representation of the T12 trunk kind of being 4 links,
Right.
equal cost, is not valid for something whose destination is L4. Just
Right.
because of the bandwidth,
Yeah.
whereas it might be if it was L3 because it is the same bandwidth in both directions.
Yeah, that's key. So in this example here, I'm just really showing off that we can do unequal cost load balancing. But in a regular normalized topology, you really wouldn't have something like this because you do a common spine and leaf, It'll be a single link from each leaf going to every single spine, so it'll be a normalized topology. But in this example, if you want to get creative and do some custom cabling, that's what it would look like in terms of what's happening in the background.
And presumably it is smart enough where if a link drops out, that path bandwidth is recalculated.
Exactly. So for every topology change in terms of links or nodes, it'll rebalance the entire, it's actually a color database, kind of like MPLS. So we got full bandwidth statistics going across the entire fabric.
Out of curiosity, does it distinguish between if you have an aggregated link, an automatically aggregated link with two links, and you lose one of them, does that become a sole straight link and stops being an aggregate? Like, or does it become an aggregated link?
Yeah, it just
simply has
becomes
one
a
channel?
regular link at that point.
So is there any interruption in traffic at that point as it shifts from being part of an aggregate interface to just
so
being
any
a straight-
packets that were already in path that happen to be going across the wire as the light goes down or what have you, those would be
Sure,
lost, but
sure.
retransmit and try again.
But for the link that remains up,
Right.
I'm just wondering if, from an implementation perspective, whether or not if you change a link from being standalone to being part of an aggregated unit, does it blip as it does that?
Oh, I see. Yeah. So as you add additional capacity to it, say it starts as a single link, then goes towards an automatic trunk or aggregate, will there be any kind of blip in that process?
Right, because as a single
Yeah.
link, it's not. I mean, we often build aggregated interfaces with a single link in them, with the view that later on, when we add a second link, it's a pretty smooth upgrade, right? As opposed to what I'm hearing here is, well, it's a standalone link unless I see a second one, in which case now I'll build an aggregated link automatically with both of them in,
Yeah.
right? Which to me is a logical change within the box and makes me wonder whether or not it blips. It's just a curiosity
Right.
point.
It's kind of like a make before break type scenario. So we ensure that it's up before sending any ingress or egress traffic across that link. So we've got to get an ACK back, basically.
Okay.
So on the forwarding, the multicast and broadcast, unknown unicast, it's basically, it relies off of our multicast. So we're doing bidirectional multicast here. And we have a multicast distribution tree per every node in the fabric. And we use the breadth first algorithm to calculate that path. So we always get the shortest, most efficient, and lowest latency link going from point A to point B in the network. And we leverage all that for the broadcast and unknown unicast. And for just regular unicast, it's just full ECMP. And we actually use the Broadcom high gig protocol within the fabric. So everything's a single lookup. And because we're using the high gig protocol, it's going to be faster than standard Ethernet. So that's how we get the low latency into this fabric. It's just basically leveraging the high gig protocol. And with that protocol, it's just a single lookup. So if there's going to be 2 or 3 intermediate hops in between, those intermediate switches really don't care about the payload whatsoever or ether types or all that stuff. It simply looks at the high gig header and simply forwards it on to its final destination.